Okay, so we just finished talking about Boyle's law, where it explains that pressure and volume have an inversely proportional relationship, where if pressure increases, volume decreases. If pressure decreases, volume increases. That's what we mean by inversely proportional. And we assume a temperature of a system is held constant. We know that temperature of a system is related to its energy. The kinetic theory of gases, it explains that the energy in particles is responsible for their movement. So, what happens to the other properties when we add thermal energy to the system that contains these gas particles? So, Charles's law discusses the relationships between temperature and volume. Remember, we're always talking about three different variables here. So temperature and volume, we also have pressure. But in this system, we assume that pressure is constant. So now we're talking about temperature and volume. So Jacques Charles, he was a French scientist who was the one who proposed this law. And he found that temperature and volume of a gas are directly proportional. So this is very different from inversely proportional. So temperature and volume of a gas are directly proportional when pressure is held constant. In other words, as temperature increases, the amount of volume required to keep the gas at the same pressure must increase as well. So if one increases, the other one increases. Directly proportional. Charles's law is expressed by this equation. So it is V1 over T1 equals V2 over T2. That is the formula. Make sure to write it down in your notes. It is important to note that in when we're writing about this law, we must use Kelvin. So Kelvin is an absolute scale, which means that we only use numbers from 0 up, meaning no negative numbers. Okay. So let's say I have this problem here, okay? So again, the formula for Charles's law is V1 over T1 equals V2 over T2. Okay, so volume 1 is initial volume. T1 is initial temperature. V2 is final volume. And T1 is, not T1. T2 is final. Temperature. Okay. So this is the formula. I'm gonna make it smaller. Okay. So if I had a problem here, I'm gonna use green, where a sample of a gas is heated from 124 Kelvin to 185 Kelvin. At 185 Kelvin, the gas had a volume of 0.743 liters. What is the initial volume? Of the gas. Ooh, that was way too low. Okay. So a sample of a gas is heated from 124 Kelvin to 185 Kelvin. At 185 Kelvin, the gas had a volume of 0.743 liters. What is the initial volume of the gas? Okay. All right. So right there, it's telling me that the initial volume of the gas. Okay. So that means that 185 Kelvin, which had a volume of 0.743 liters, are our final variables. So again, V1 over T1 equals V2 over T2, which can also be written as V initial equals V final. Okay. But I'm going to keep it as V1 over T1 equals V2 over T2. So we have V1 initial volume. Nope. That's what we're looking for. We have V2 final volume. Yeah. 0.743 liters. Do we have the initial temperature? Yes. We have a range right here. So this range tells me that 124 Kelvin to 185 Kelvin. So that's my range. The initial temperature is going to be 124 Kelvin. And the last number, or the final temperature, is 185 Kelvin. So I have my numbers. Now I'm just solving for V1. So that means I need to rearrange this a little bit. Okay, so V1 over T1 equals V2 over T2. And I'm solving for V1, which is this one, which means I need to leave this variable alone on the left-hand side, which means first I must multiply these two to get rid of T1. So I'm going to multiply T1, multiply T1. This one cancels, leaving me with V1 equals T1 V2 over T2, which means we're multiplying these two and then dividing by the second temperature. If we proceed by substituting the given values, then we have V1 equals 124 Kelvin by 0.743 liters, and we divide by 185 Kelvin. The K's cancel out, just like we canceled out the temperatures here. These variables will be crossed out, canceled out. And my last number, after I calculate it here, so 124 times 0.743 equals, divided by 185 is 0.498 liters, and that is my initial volume. And you can manipulate the equation for Charles's law in a similar way to solve for all the other variables. So right now we solved for V1. You can rearrange the formula to solve for V2 if you needed it, and if you were given V1, T1, and T2. So it's a very useful formula, and it explains the relationship between temperature and volume pretty well, assuming that pressures remain constant. So